Hi, so we're back and we're kind of finished with a brief overview of the basics of fluid dynamics. If you recall, we've laid down the basic equations that of mass, momentum, and energy conservation. We didn't spend that much time on energy conservation, but nonetheless, and we spent a fair amount of time talking about the momentum equation, various guises thereof, and after all this, you see, now we're ready to sort of take the plunge and move forward and look at various applications of these equations, having laid down the basics. One of the main things I thought I would emphasize now is the concept of dimensionless numbers. Dimensionless numbers in fluid dynamics, right? Essentially, it boils down to, you remember when we wrote down the Navier-Stokes equation, there were several terms. For instance, we had the gradient of pressure term, we had the viscous term, which looked like so on and so forth, right? So the question is, are each of these terms, do we have to retain all these terms in every situation? Or are there situations where I can throw away one term in favor of another? For instance, if we are talking about an inviscid situation, if we are talking about a situation where viscosity is not important, clearly I can throw away this term, this is not important, right? But we have to, while doing physics, we have to qualify these things a little more. What do you mean by not important? Not important with respect to what, right? So here, clearly, since both of these terms were appearing on the right-hand side of the Navier-Stokes equation, we would have to say, well, if I want to throw away the viscosity term, if I claim that viscosity is not important, then this term had better be negligible in comparison to this term or some other term, right? So we would have to compare terms, and this is where the concept of dimensionless numbers comes in. It serves as a very good aid to figuring out what term is important, what term is not important, and that kind of thing. There are also some other issues like dynamic similarity. Which I'm simply saying this word right now, but I won't bother explaining it for the time being. But this is also something that we will concentrate on in this part of the course, right? And the reason I'm mentioning both of these in the same breath is because the concept of dynamic similarity is very closely related to that of dimensionless numbers. Okay, now. Underlying this whole thing about, so we will start with this. We will start with talking about dimensionless numbers. There are several. I will only start talking about a few right now. And underlying this whole concept of dimensionless numbers is the familiar concept of dimensional analysis, which you must be familiar with, doubtless. Which is simply saying, well, what are the dimensions of speed? Well, the dimensions of speed are something like centimeter per second or L(t) raised to -1, so on and so forth. Okay, so it's really closely related to the very familiar concept of dimensional analysis, which I'm sure many of you have been using for a long time. So this is just to put you at ease. This is really several of these dimensionless numbers simply arise from a dimensional analysis. So without wasting much time, let's get right to it. Consider the now familiar Euler equation, right? Well, actually, not quite the Euler equation. Let's say the Navier-Stokes equation, which includes viscosity also, which you recall is nothing but F equals ma, right? So written in the Lagrangian framework, it's a little more compact to write it that way. In other words, if you recall, the Lagrangian framework is one where you are sitting on top of the fluid parcel. Remember that, right? So, in terms of the Lagrangian framework, the Navier-Stokes equation is simply rho m a, yeah, is equal to, and the f's are minus, if there is a gradient of pressure, right, plus mu this is a vector Laplacian. I want to beg your pardon, I didn't write this very well, sorry. Yeah, this is a vector Laplacian. Yeah. Now, the mu is the coefficient of dynamic viscosity. Many times we write mu as the density times this, and this is also often, confusingly, both of them are often called the coefficient of dynamic viscosity. The distinction I want to make is that the dimensions of this are something like centimeters, I seem to be making several writing mistakes today, like that, okay. I'm not sure that's right. Let me leave it as it is. It is the dimensions of it, the nu has the dimensions of the coefficient of dynamic viscosity divided by mass density, and this is simply the dimensions of this are simply grams per. Okay, so and in terms of this, if you write it this way, then this can equivalently be written as right. That's obvious. So now, what are these different terms? Well, this is ma. This is the pressure gradient. The fluid's flowing because there's a pressure gradient. There's a high pressure here, low pressure there. Fluid flows under the influence of the pressure gradient, right? And this is the viscous term, which represents rubbing together of layers, and so that's what it is, and it contributes to momentum transport, of course. That's why it's in the momentum equation, right? And we've also seen that you can bundle both of these together, both of these terms together into one pressure tensor. We've discussed all that, but for the time being, this is a more convenient way of representing the Navier-Stokes equation, because especially for what we want to discuss right now. Yeah. So now, as we said earlier, the question now is, how do I decide which term is, in a given physical situation, can I throw away one of these terms? For instance, can I assume that is it justifiable for me in a low viscosity situation to simply throw away this term, so that I'm only left with these two? You realize, of course, I'm not including body forces like gravity. So that's neglected for the time being, just for simplicity, right? So if, for instance, I was to throw away this term, you would have to compare it. You would have to compare this term with this term, or compare this term with this term. And that's exactly what we're going to do, right? So before that, let's write down what's called the order of magnitude of these terms. Let me again repeat this. Let me repeat the Navier-Stokes equation for a minute. It's important to have this on the same slide as what we are writing things down. So I thought right. So now, what is, I claim that this term is of order rho v over t. Now, this is essentially dimensional analysis. Whatever the dimensions of rho are, grams per centimeter cube, that I keep that as it is. Now this dv dt is something like some kind of velocity divided by some kind of time. Now I realize it's a little vague, yeah. What do you mean some kind of velocity? What do you mean some kind of time? A representative velocity, okay. When you're talking about a breeze flowing through this room, you're certainly not talking about a breeze, something flowing at several kilometers per second. No, you're talking about velocities that are much smaller than that. So, of the order of so many centimeter per second, that kind of thing. So, that is what I would call a characteristic velocity for a given situation. Similarly, one can arrive at a characteristic time scale, right? How fast do you think, do you expect things to change in this room? Yeah, do you expect things to change over the time scale of seconds, or do you expect things to change over the time scale of hours? Okay, if you ask these questions, you will very quickly be able to come up with a reasonable time scale. Okay, so this is what we call a characteristic time scale. Okay, so although this concept is a little vague, it still makes sense, right? It still makes sense to talk about a characteristic velocity and a characteristic time scale. And so using these concepts, we can say that this term is of the order of rho times v over t, this term, right? Let me now write down this term. I'll leave this for later. We will talk about this in a minute. So this is of order. I leave these two terms as it is. Okay. Now remember, this is a second derivative, right? It's like d square v dx square or d square v dz squared, so on and so forth. So it's essentially velocity divided by some length scale squared, right? This is something like that, right? So it is some kind of characteristic velocity divided by some kind of characteristic length scale squared. That's the order of magnitude of this term, right? I might simplify this by saying that v over t is something like of the order of rho. I can say this too, right? This is the same as this, in that the t I'm writing as a v over L. Okay? Just because I want only v's and l's all throughout the equation, I don't unnecessarily want to introduce a t if I can help it. In this particular case, I can, right? So now we come down to this term now. What is this, roughly of the order of? I claim that this is of the order of rho. Well, I'm introducing a new term called cs squared, right, which is the speed of sound. We will discuss the speed of sound. This is something that's central in fluid dynamics. We will discuss this in some detail a little later. But as of now, I'm sure you've come across this definition. The speed of sound is, okay, and a little dp d rho, right? That's a speed. And so carelessly we can write this as p over rho. Okay, so instead of p, I write rho times cs squared. That's all I've done here. Okay, so I've written this, rho times cs squared gives roughly p, yeah, and this is a gradient, so it's like a d over dx kind of term. So that I simply write as d over dx is 1 over L, where L is some characteristic length for the dimensions of this room, for instance. Characteristic length would be something like a meter, certainly not a millimeter, okay, and certainly not a megameter. It's of the order of a meter. So that's what I mean by characteristic length, so I plug that in. So please remember this when we go to the next slide. These are the orders of magnitudes of these three terms. Now we are in a situation to say, well, if I claim that this term is smaller than this term, or this term is smaller than that term, then all I need to do is essentially divide this by this, for instance, to compare the magnitude of this term to this term. And this gives rise to the concept of dimensionless numbers. Okay? Complete this. this is the speed of sound. We will discuss this in great detail as we go along, but for now I have just introduced it this way, right. Let us now, so this would be term 1, term 2 and term 3. Okay. So, now the ratio of term 1 to term 2. Okay. In other words, the term 1 you see is what one would call the inertial term. Okay. This is what represents inertia, ma, by Newton's second law, that is the inertial term. So, I would say the ratio of the inertial term to the pressure gradient term right, the inertial term to this pressure gradient term, that would be some rho v squared over L divided by rho Cs squared over L, right. So, in other words, this is something like the dV dt term over the gradient of pressure term. Okay. This is of the order and this simply follows from this and this, okay, because the L's cancel out, and so and the rho's cancel out also. So, all you are left with is V squared over Cs squared. Okay. So, this one, and this very important quantity is called, is often denoted by the letter m, and this is something that is called the Mach number. This is the first dimensionless number that we will encounter, the Mach number. As such, you see the Mach number is simply the ratio of the flow speed, more accurately not really the ratio of the flow speed itself, the ratio of some characteristic speed in the system. Okay. Divide, well, the square, this is actually the Mach number squared, I beg your pardon. This is, let me just erase this a little bit. Yeah. So, this is the square of the Mach number, this whole thing. Okay. So, the ratio of the flow speed to the sound speed is called the Mach number. Okay. But where did it come from? Why did I simply pop it on you? It came from this fact, is the ratio of the first term in the Navier-Stokes equation to the second term in the Navier-Stokes equation, or the ratio of the inertial term to the pressure gradient term. So, clearly if the Mach number is large, that means the inertial term is more important than the pressure gradient term, and vice versa. If the Mach number is low, then the pressure gradient term is more important than the inertial term. So, this dimensionless number, that this is the first dimensionless number we are encountering, and this gives you a good idea of which of at least these two terms are relatively more important than the other. So, this is our first encounter with and this is how it comes about, right. So, another example, the ratio of the first term to third term. Again, first term to third term, right? Inertial term to viscous term. In other words, over viscous term, which is essentially the rho dV dt over rho nu, right. The ratio of these two terms is Notice this is of order rho v squared over L, and this is of order rho nu v over L squared. Obviously, the rho's will cancel each other, right? So therefore, this turns out to be of order v L over nu. This is essentially some characteristic velocity in the fluid times some characteristic length scale in the fluid flow to be precise, and this is the coefficient of dynamic viscosity. And this term is another dimensionless number. You can verify that this is dimensionless indeed. You can verify that there are no dimensions, the dimensions are 0. Okay. And this term is something called the Reynolds number. Another very important number in fluid dynamics, the Reynolds number. Okay. This gives you, the Reynolds number gives you the ratio of the inertial term to the viscous term. If the Reynolds number is large, the viscous term is relatively speaking negligible. If the Reynolds number is low, then the viscous term is quite important. So this is how these things come about. So we will stop here for the time being, and we will take this philosophy of these terms a little farther. What I will do is I will instead of writing things down, instead of invoking these terms in a systematic fashion as we have done now, I will simply list out a few other dimensionless numbers that are commonly used in fluid dynamics, and then we will go on. So.